Hey guys, this is Math 116, section 6.3. Now we are looking at the future value of annuities. So this word is annuities, and an annuity is a financial plan characterized by regular payments. Think about a savings plan where you're putting in money and it's accruing interest. And so now they want to look at the future value. So how much, if you're putting money on a regular basis, how much is it going to be worth in the future? So question number 9, section 6.3. Find the future value of an ordinary annuity of $80 paid quarterly for 3 years if the interest rate is 8% compounded quarterly. Oh my goodness, so many words. Okay, one thing to point out. This says an ordinary annuity. It's ordinary. That means we are making the payments at the end of the month or at the end of the quarter. So ordinary annuity means at the end. You're putting your payments at the end. So $80 every quarter for 3 years, and it's compounded quarterly. Well, in order to solve this problem, we're going to use this formula. You're definitely going to want to know this formula. Page 393, the future value of an ordinary annuity, so you're paying money at the end of each period, is given by this formula. The future value S equals R. That's the money you're putting in each period, so each quarter, each month, whatever. I is the interest rate per period, so I'm going to show you how to deal with this one. N is the number of periods, so how many months are you putting it in, how many quarters, whatever. So you got just 3 things here. Amount of money you're putting in each period, so the period could be a month or a quarter or a year, whatever. Number of periods and the interest rate per period. So there's the formula. Back to the question. Find the future value of an ordinary annuity, $80, paid quarterly for 3 years. Interest rate is 8%, compounded quarterly. Let's go. Let's get this one. So here we go. Question number 9. So in this case, R, which is the amount of money we're putting in at the end of each month, is $80. We're putting in at the end of each, actually it's quarter, end of each quarter. And a quarter is 3 months. So every 3 months. Every 3 months. The interest rate, check this out, is 0.08. That's the annual rate divided by 4 because we have its rate per quarter. We're doing the interest rate per quarter. So this is the annual rate. That's the annual rate. And 4 times a year. So the interest rate we're going to use is 0.02. And N, which is the number of periods, right? How many times are we going to be putting in $80 is going to be 3 years times 4 quarters per year, right? So that's going to be 12. 12! And now we use our formula. What could be easier than that? S equals, this is R, the formula, times 1 plus I to the n minus 1, all divided by I. So this is going to be equal to 80 times 1 plus 0.02, right? Because our interest rate is quarterly, the quarterly interest rate, that's I, raised to the n, which is 12 minus 1, all divided by 0.02. So in this problem, I think finding n and I is the little tricky part. So this all is $1,072 and about 97 cents. So approximately, that little dot means approximately. So for this one, what is the future value? You're putting $80 away every quarter for 3 years. So every 3 months, you're putting $80 away. That gives you $1,072 at the end of 3 years. So I'll say in 3 years. Let's look at another one. That wasn't so hard. Okay. Future value of ordinary annuity. So again, we were paying at the end of each period. Question number 13. We put $2,500 at the end of each quarter. At the end. At the end means ordinary annuity. Ordinary. Ordinary. Thanks, spell check. So $2,500 in an account that earns 5% compounded quarterly. After how many quarters will the account contain $80,000? So in this case, they switched it up on us because we now know the future value. This part here, $80,000, that's the future value. So here's what we know. We know the future value is $80,000. We know R, the amount that you're depositing each quarter, is $2,500, right? $2,500. We know the interest rate is 5% compounded quarterly. So it's 5% divided by 4. I can do that. That's equal to 0.0125. So what we don't know is N, which is the number of periods. I'll bring this up a little bit. So what we want to know, it says after how many quarters? This is the question is asking essentially what is N? After how many quarters? So we're going to use the same formula for the ordinary annuity, and we're going to solve for N. Okay, so we have all these things, we just don't have N. But you're saying, oh no, N is in the exponent. Yeah, it is. That is so true. You are right about that. Question number, what was that one? 13. So here's what we got. We have S, future value is $80,000. R is equal to $2,500. I'm turning into my golf announcer voice. I is equal to 0.05 divided by 4, which is equal to 0.0125. Interest rate. So again, we're dividing it by 4 because it's quarterly. We're putting it in each quarter. And now we have we don't know what N is. So here's the formula. We have S is equal to R times 1 plus I raised to the N minus 1 divided by I. That should be a song. We have 80,000 equals 2,500. I'm plugging in. That's S. That's R. Equals 1 plus 0.0125 raised to the N. What's N? We don't know. Minus 1, all divided by 0.0125. Well, that's a mess, isn't it? A little bit, but we can do it. So the first thing we're going to want to do, now we're doing essentially just an algebra problem. We're going to divide both sides by 2,500. Or this by 2,500, right? That goes away. Multiply both sides by 0.0125. Right? Times 0.0125 over here. So those go away. We'll add 1. Add 1 there. So that goes away. So what we are left with is on this side, this whole thing. So 80,000 divided by 2,500 times 0.0125, take all that, then add 1, is equal to 1.4. You should get 1.4 by all this stuff. So that's going to be equal to this piece, which is 1.0125 raised to the N. Now I'm going to go on to the next page so I can deal with this N, because we're trying to solve for N, which means it's, oh no, an exponential problem. So here's where we were. 1.4 equals 1.0125 raised to the N. Well, how do we get rid of that N? We're going to take the natural log, and that will bring it from the exponent down in front. So you can take the natural log of both sides. What? We did this in chapter 5. We did it for a reason. So we could solve exciting annuity problems like this. So I just took the natural log, let's get rid of that, of both sides. Now, remember the natural log rule. N can come in front. N, it's the exponent. A natural log of an exponent. The exponent gets multiplied in front. Natural log 1.4. So now we have N. I can divide both sides by natural log of natural log 1.0125. So we got natural log, divide this side, natural log 1.0125. I'm going to go faster. 1.4 divided by the natural log of 1.0125. So this you plug into your calculator. So you're not going to want to do that with your, in your mind or with a log table. The answer is 27.1. And this is 27.1 quarters. So, I don't know. How many years is that? 6 years? Like 6 to 7 years? Anyway, 27.1 quarters, because N is the number of quarters. And if we go back and look at the problem, it said after how many quarters? Well, the answer is after about 27.1 quarters. I think the book just gives 27.1, which is sort of ignoring the mess that is, doing all this and then having to solve for N. So let's look at another one. There's another type of annuity. This one. Question 19. Find the future value of an annuity due, this is a new word, of $100 each quarter for 2.5 years at 12% compounded quarterly. So what they're saying is at the beginning. So when you make a payment at the beginning of each period, so not at the end. For an ordinary annuity, it was at the end, but for an annuity due, it's at the beginning. So at the beginning of each quarter, you're paying $100 for 2.5 years at 12% compounded quarterly. So your payments are made at the beginning of each period, and here's your formula. Really, the only difference is if you're paying at the beginning of each period, you have one extra period, so you get this extra multiplication thing. So, same sort of formula. N is the number of periods, I is the interest rate, and R is the money you're depositing at the beginning. So whether or not you're making the payments at the beginning or the end will decide which formula you're using. Annuity due, beginning. Due at the beginning. It's doing at the beginning of each month. Okay, let's do this one. Let's do it. We're going to do it. I'm going to use yellow. Come on, yellow. Question 19. So here's our formula. The future value, at the very end, the total money we'll have. This is the R, is the amount of money we're putting in at the beginning of each whatever month or quarter. It's the interest rate per period, number of periods, interest rate times 1 plus I. So here's what we have. R, that's we're putting in $100 at the beginning. I is equal to the annual interest rate divided by 4 because we're compounding quarterly. The problem said that. It said compounding quarterly. That means every, 4 times a year, every 3 months. So 0.03 is the interest rate. And N, which is the number of compounding periods, number of periods, so we're compounding quarterly, so that's going to be 4 quarters times 2.5 years is equal to 10 periods. Do you see that? So here's our formula. It's going to be equal to 100, that's R, times 1 plus 0.03 raised to the 10, N is 10, minus 1, all divided by 0.03. That whole thing is a bracket, and multiplied by 1 plus 0.03. Whew! You're going to want calculators for this. And this all equals about $1,180.73. S due. So again, the difference in this problem is you are paying at the beginning of each month, or each, in this case, every 3 months, each quarter. So, back to this problem. So find the future value of an annuity due. Annuity due means the beginning of each period. You use this different formula. I have one more problem to go over with you. Mr. Gordon. We got to talk about him. Question 33. Mr. Gordon plans to invest $300 at the end of each month in an account that pays 9% compounded monthly. After how many months will the account be worth $50,000? Oh, that'll be a happy day for Mr. Gordon. So here's what you want to pop out. He's going to put $300 at the end of each month. At the end. So does that mean it's an ordinary annuity or an annuity due? Well, it's at the end of each month, so we know it's an ordinary annuity. It's an ordinary annuity. And we know the future value. We want to know, we know that it's going to be $50,000. We know the amount that he's depositing at the end of each month is $300. We know his interest rate per month is going to be 9%. That's the annual rate divided by 12 months is 0.0075. But we don't know the number of periods. So we're saying after how many months? This is what is N, like that. So again, this is similar to question 13. We're going to use this formula for the future value of an ordinary annuity, and we're going to solve it for N. Oh no, does that mean more logarithms? Yeah, it does. It does mean more logarithms. We're lucky that way. Question number, what's this one? 53, 33? Can't read my writing. 33. So here's the formula. We have S is equal to R. Remember that he's paying at the end of the month, 1 plus I, raised to the N minus 1, all divided by I. This is the ordinary annuity, ordinary annuity formula, because he is paying at the end. So now we're going to plug in numbers and solve for n. I'm going to do it fast. So I have $50,000, that's S, is equal to $300, it's R, times 1 plus 0.0075, that's I, raised to the n. We don't know what n is, so I will leave n as n. And now we're going to do just like we did on the other question, multiply everything by 0.0075. That's going to cancel that. 0.0075. What you do to one side of the equation, you have to do the other. Divide this side by 300. That goes away, so we have to divide this side by 300. And then you add 1. Add 1. So we get this whole big messy thing, and then when you're done, you add 1. And all this side equals 2.25 equals, just we're left with this, that's the only piece, because the plus 1 minus 1, we canceled those. Okay. 1.0075 raised to the n. We're solving for n. How do you get n out of the exponent? Are you thinking natural logs? That's what I'm thinking. So we have 2.25 equals 1.0075 raised to the n. So I'm going to take the natural log of both sides, and this gives me, I'm skipping the step, n times natural log of 1.0075, because the n can go in the front of the natural log. So n is equal to natural log of 2.25, divide both sides by natural log of 1.0075, a number that we all have handy. I'm kidding. So all of this is equal to, you plug it into your calculator, well, 108.53 months. That's all. That equals n. Good job, Mr. Gordon. Mr. G's money. So the questions, going back to the question. Mr. Gordon plans to invest blah blah blah. After how many months will it be worth $50,000? After 108.53 months. That's all. He hardly has to wait any time at all. Anyway, so that's how you do these problems. You want to focus, the main takeaways here are a ordinary annuity. It's due at the end of each month. For an annuity due, it's due at the beginning of each month. And sometimes if you want to know how many months or how many periods, then you have to do this business where we took the natural log. You might end up solving for n, and when you get to this part, you have to take the natural log. So that should carry you through what you need to know for section 6.3.